All right, let's just jump right in with a huge question. Have you ever just stopped and looked around at, well, everything, and wondered, how does any of this work? I mean, what is life, really? We're going to dive into that today, but from a really interesting perspective of physicists. We're talking about Erwin Schrödinger, one of the founders of quantum mechanics, and his amazing 1944 book, What is Life?
Okay, so let's start with the central puzzle, the big problem that Schrödinger was trying to wrap his head around. You've got this fundamental law of the universe, right? The second law of thermodynamics. It basically says everything trends toward disorder, toward chaos. Physicists call this entropy. But then you look at life. And what is life? It's a masterpiece of intricate, mind-boggling order. So how do you square that? How can life even exist?
And because he was a physicist, Schrödinger couldn't just leave it at, wow, isn't that weird? Nope, he had to dig deeper. He asked a really fundamental question. Can this stuff happening inside a living thing, all the complex processes, be explained by the physics and chemistry we already know? Or is there something else going on? This is where things get really interesting. It's like you've got these two opposing forces. On one hand, physics is telling us everything should be falling apart, getting more random. But on the other hand, you have life. And life doesn't just, hold the line against chaos. It seems to be actively fighting back. It's not just maintaining order, it's creating more of it. It's just wild. So, where do we even start to solve a puzzle this big? Well, the first clue, surprisingly, didn't come from physics. It came from biology, specifically from looking at how traits are passed down from one generation to the next, the mechanism of heredity. Schroedinger came up with this fantastic metaphor for chromosomes. He called them the hereditary code script. I love this because it's so perfect. They're not just the architect's plan, the blueprint for an individual. They're also the builder's craft. They carry out the plan. It's the whole shebang in one package. And of course, we now know he was talking about DNA, but it's amazing how close he got just by thinking it through. And this brings us right to the heart of the contradiction. On one hand, this genetic code is unbelievably permanent. It gets copied almost perfectly for centuries. But on the other hand, the thing doing the copying, the gene, is tiny, like ridiculously small, just a few million atoms. So how can something so small, made of so few parts, be so incredibly stable for so long? From a classical physics point of view, it just doesn't make any sense. Right. So if you're looking at this through the lens of classical physics, the physics of our everyday world, this stability is a real head-scratcher. Why? Because most physical laws that we experience aren't absolute. They're statistical. They're all about the law of averages. Think about it like this. Every single atom is just constantly jiggling around in this random, chaotic dance. Physicists call it heat motion. The only reason we get predictable laws like the pressure in a tire is because we're looking at the average behavior of trillions and trillions of atoms. It's the sheer number of them that smooths out all the chaos into something predictable. Okay, and this is the key. There's this rule in physics, you can call it the square root of n rule. Basically, it says that the more particles you have, that's n, the more accurate the law is. The error shrinks as n gets bigger. But for a gene, n is super small, and a small n means a huge potential for error. So based on this, a gene's behavior should be all over the place. It should be totally random and chaotic, not this pillar of stability we see. Schrödinger really hammered this point home with a great thought experiment. He said, heavens, what would life be like if we were so sensitive that the random movement of a single atom could affect what we see or feel? It would be pure chaos. You couldn't have orderly thought. You couldn't perceive anything reliably. Life, to even exist, absolutely requires a stable world, and that means stable building blocks. So where's the answer? If classical physics can't explain the stability, what can? Well, the solution to this whole paradox isn't found in the world of big numbers and statistics. It comes from the much weirder, much more fascinating world of quantum mechanics. And here's the secret. Get this. The gene isn't just a random pile of atoms. It's a molecule, a large, stable molecule. Its incredible stability doesn't come from the law of averages. No, it comes from something way stronger, the powerful chemical bonds holding its atoms together. And guess what explains those bonds? Quantum theory. Now, this analogy is just perfect for understanding the difference. In the old classical way of thinking, it's like a ball on a ramp. Any little nudge, any bit of heat motion could change its position.
But in the quantum world, it's like a ball on a staircase. It's stuck on one step. To move it, you don't need a little nudge. You need a big enough kick of energy to get it all the way up to the next step. That's a quantum jump. And that's why molecules are so darn stable.
This all leads to Schrodinger's big idea, his key insight. He coined this amazing term, the aperiodic crystal. Just think about what that means. It's a crystal, so it has that rock-solid stability, but it's aperiodic, meaning it doesn't have a simple repeating pattern like a salt crystal. It's more like a complex tapestry, where every thread is different. And that complexity is what allows it to store a huge amount of information. So what are mutations? They're just those rare quantum jumps when the molecule gets kicked into a new stable state.
All right, so let's zoom back out. What does all this quantum stuff actually mean for life? Well, it points to something really profound, a new kind of principle. The big takeaway is that life doesn't actually break the laws of physics. It just plays by a different set of rules.
This is the real game changer in his thinking. You've got two ways of creating order. Non-living things create order from disorder. You take a bunch of chaotic jiggling atoms, and predictable laws emerge from their average behavior. But life does something completely different. It works on the principle of order from order. It takes a highly ordered structure, that gene molecule, and uses it to build more highly ordered structures.
But wait, what about that pesky second law, the one about everything falling into chaos? How do we avoid just decaying? Well, this is where Schrodinger's idea of negative entropy comes in. It's a brilliant concept. To stay ordered, life has to constantly feed on order from its environment. That's what you're doing when you eat complex food molecules. You're essentially eating order to pay off your entropy debt and keep your own internal order going.
So let's bring it all together. What should you take away from this? Well, life's amazing stability seems to defy the laws of physics, but it doesn't. The gene is so stable because it's a huge molecule ruled by quantum mechanics, not statistics. Schrodinger's term aperiodic crystal perfectly captures how it can be both stable and full of information. And maybe most importantly, life works on this incredible principle of order from order, using an existing code to build new life. What Schrödinger really did was show that life doesn't break the rules of physics. Instead, it might be pointing us to new rules we haven't even discovered yet. He argued that life seems to operate on a different kind of physical principle. And that leaves us with a really provocative thought to end on. If order from order is one new principle, what other laws of physics are still out there, just waiting for us to find them?